Let's take a look at the top 5 most common mistakes when designing with CMOS logic specific to the inputs of the devices. Number 1 is slow input transitions. Specifically, we're talking about how fast the input transitions from the low state to the high state or from the high state to the low state. Faster is better with CMOS. Next up is incorrect input voltages. Really, I think this is related to misunderstanding datasheet specifications, so we're going to go into some details on that. Next is incorrect termination of unused pins. We see this most commonly whenever there's a bunch of channels, for example, an 8-channel buffer, and some channels are going to be unused, and then the connections are just left open. I'll talk about why you need to terminate unused input pins correctly. It's not uncommon to see pull-up and pull-down resistors used incorrectly or sized incorrectly for a particular circuit. And last but not least, it's common to see a lack of ESD protection. Although most logic gates have some built-in ESD protection, it's really not intended for system-level applications, and we'll talk about that a little bit more. Instead of trying to explain each of these individually, I'm going to show you the structure of a CMOS input, and along the way I'll explain how to avoid each of these common mistakes. The specific device that I'm going to be using is an inverter, and I'm going to be using that because it has a very similar design to every other CMOS logic gate, and it's the simplest. Let's take a look at what's going on inside of this. All it is a pair of MOSFETs. I'm using a simplified MOSFET symbol. For the PFET, the body is implied to be connected to VCC, and for the NFET, the body is implied to be connected to ground. This is the simplest circuit that can be made in CMOS logic. In the case where the input is 0 volts, then VGS for the NFET is 0, and VSG for the PFET is VCC. So the PFET is turned on, the NFET is turned off. That means the output is going to be VCC. When the input is biased to VCC, the NFET is turned on because VGS is VCC, and the PFET is biased off because the VSG is 0 volts. That means that the output is going to be 0. In addition to having this simple CMOS circuit inside of an inverter, quite often, this circuit will be repeated. Rather than drawing it again, I'm just going to draw the inverter symbol here. But you can just imagine that that same circuit is repeated 2 more times. This is what's called a buffered inverter. There may be more than just 3 stages. It will depend on the device, how it was designed, and its application. However, the operation of it is pretty much the same regardless of how many stages there are. And specifically today, we're going to be looking at the input, so we're really worried about what's going on this side, not so much what's going on past this. Looking a bit closer at the input, there's actually a little bit more going on over here. Very commonly, there's going to be an ESD diode connected to ground that's going to allow discharge of ESD events. Additionally, there could be ESD diodes going to VCC. And there's actually 2 different types that are common. One is a clamp diode that's going to connect directly to VCC like this. And another would be back-to-back diodes, where you would have a diode like this connected directly to another diode and then to VCC. This is typically what's going to be used in an overvoltage tolerant device, something that allows you to have the input higher than VCC. And this is what's going to be used in a device that clamps input voltages to VCC. For an example, let's take a look at an HC family AND gate. This is the 74HC08 from Diodes. In the recommended operating conditions, we can see that the input voltage is recommended to go from 0 volts up to VCC. This is a subtle hint that this device has a positive clamp diode. so it's not using that structure. If the input is larger than VCC, so let's give ourselves some numbers here. If VCC is 5 volts, for example, and our input is 6 volts, then this diode is going to be forward biased. It has a larger voltage on this side than it does on this side, and that will allow, essentially, infinite current to flow. When we go back to the datasheet, we can see that it lists an input clamp current, IIK. One common error that's made is that some engineers think this means the input will clamp the current to 20 milliamps. In reality, this is saying that you should never exceed 20 milliamps through that clamp diode. In our case, connecting 1 volt directly across this diode, it's very likely that that 20 milliamps will be exceeded and the device will be destroyed almost immediately. In order to protect the diode, it's pretty easy. All you have to do is add a series resistor. As long as the resistor limits the current to less than 20 milliamps, then this diode will survive. Then you only have to worry about that current flowing back into your supply, and that might be a topic for a different video, but some supplies don't like it when current flows back into them. Similarly, if the input voltage were to go negative, as shown here with Vin being less than negative 0.5 volts, then the negative clamp diode could be turned on, and the current would flow the other direction through the other diode. Note that this has plus or minus 20 milliamps in the datasheet. That indicates that current can flow into or out of the device. Now let's go see if we can find a datasheet that does not have a positive clamp diode to see the difference. This is the datasheet for the Nexperia 74LVC1G04, which is a single inverter. Looking down into the recommended operating conditions, we can see that the input voltage says 0 to 5.5 volts. It's no longer limited to VCC. Going back to the limiting values table, which is typically absolute maximum ratings in other datasheets, we see that the input clamp current is only valid for negative current values and when Vin is less than 0 volts. This indicates that there's only a negative clamp diode. This negative value means current is flowing out of the device. Whenever we look back at our drawing here, that means current is going through this diode and out of the pin this way. Knowing how to read this table can really save you a lot of time whenever you're trying to understand how a logic gate works and whether you can drive an input voltage above or below a certain value. One thing that's important to bring up whenever we talk about the ESD protection on the input of a logic device is that the logic ESD protection is very weak. Let's take a look back in that same datasheet. When we go back to the front page and look at the ESD protection, it lists HBM at only 2000 volts. That may sound like a lot if you're not familiar with ESD protection, but standard system level protection diodes are going to protect from 8 kV or more. This is definitely not enough ESD protection for system level applications. In other words, if the inputs to your logic device are running directly to a port that goes outside of your system, and humans will be able to interact with this port, then you definitely want to add some level of ESD protection external to the device. I'm not going to go into extreme detail on ESD protection here. It's just important to know that logic devices aren't good enough to provide the system level ESD protection that you need. Now it's important to also mention that as long as you have your ESD protection external for any external ports that humans can interact with, it's perfectly fine to not have ESD protection on internal logic. So if you have some sort of logic function going on inside of your device, as long as none of these pins connect directly to the output of your system that goes out to the real world, then there's no need to add ESD protection in between these. The purpose of the ESD protection that's provided on a standard logic device is just for manufacturing. So when the machines and people are placing these components and soldering them down, the minor amounts of ESD that could get transferred into these devices during the manufacturing process don't cause any damage to them. Getting back to the functionality of this inverter circuit, let's look at what happens whenever the input is not exactly what you would expect it to be. What we talked about earlier were the two standard conditions: if the input is at 0 volts or if the input is at VCC. But what happens if the input is somewhere between these two? After all, normal signals are going to transition between these two states, and they may not actually make it all the way down to ground or all the way up to VCC. So what happens in the event that they don't make it all the way to the top or all the way to the bottom, and what happens if the signal is too slow? So let's just look at it from the circuit perspective first, and then we'll look at the datasheet specifications. This is the control voltage for this bottom MOSFET, or VGS. And this is the control voltage for our PFET, VSG. When the input is close to VCC, this VSG is close to 0, and that means this is going to be turned off. Now, the larger this VSG gets, or in other words, the lower this input voltage gets, the more this PFET will turn on. So for the sake of our explanation here, let's replace VCC with a specific voltage. And let's say that the threshold for each of these devices is 1 volt. So we're going to just call VT equal to 1 volt. So in the event that VSG is larger than 1 volt, then this PFET will be turned on and will allow current to flow through it. Now, if the input is 4 volts, that means that this device has just started to turn on. When we look at the PFET has 4 volts for VGS. That also means that it's turned on. And in fact, it's turned on quite a bit. So current is going to be allowed to flow through this as well. And in this case, all the way from 4 volts all the way down to 1 volt, then we're going to see that current can flow through both of these devices, and we get something called shoot-through current. And that's current that flows all the way down through both devices straight to ground. And this can be damaging current. You don't want this to happen in a CMOS device. And this is why datasheets are going to specify that you need a very fast transition from low to high for a CMOS device, rather than a slow transition. Let's take a look at a plot of what we would expect the current to look like as you transition the input voltage. So we're going to say this is our input voltage over here, and this is our current, ICC, or the current flowing from the supply down into the device. Whenever the input voltage is close to the rail, less than 1 volt or less than the threshold of this device, we expect ICC to be approximately 0. And it will be very close to that. As we pass that first threshold, we'll see that the PFET is turned on all the way, and the NFET will really control how much current can flow. Current will spike up very high in the middle when both devices are turned on to their maximum extent, and then the PFET will start to turn off as the voltage continues to increase, and eventually the PFET will turn off completely when we get to that threshold value, all the way up until we get to VCC up here. So this is a very common curve to see for the input versus ICC of a logic device. And generally, you're going to want to avoid getting into this range of operation for any type of CMOS input. Let's take a look at the datasheet. In the recommended operating conditions, we see this delta T, delta V specification. It says input transition rise and fall rate. It says that the slowest transition rate can be 10 nanoseconds per volt. Or in other words, at 5.5 volts, it must take less than 55 nanoseconds to transition completely from low to high. In the static characteristics, it shows that the input high voltage, or VIH, at 4.5 to 5.5 volts is 0.7 times VCC. So for our 5 volt supply, that means it's 3.5 volts. And that means that upper voltage here is 3.5 volts. We want to be above to make sure that we're in the high state. VIL says that it's 0.3 times VCC, so that's 1.5 volts in our case. So this would be below 1.5 volts. So between 1.5 volts and 3.5 volts, the input is in an unknown state. And you really want to switch through this very quickly. That's why you have that input transition rate. Looking at it from the waveform, we would have our VIH somewhere around here, so we need to be above that value in the high state, and our VIL below here, and we would need to be below this in the low state. This is where we're transitioning very quickly between low and high. The datasheet has one additional interesting point about this power curve. Looking in the static characteristics again, we see delta ICC, or additional supply current. For each input pin, the supply is set to any value between 2.3 and 5.5, with the input held off the rail by 0.6 volts. So that means we're operating somewhere close to here, right where that MOSFET is starting to turn on. With the output current set to 0, that just means that we're not measuring any output current coming from the supply. We're only measuring the current required to keep the device running. In this state, the current can be up to 500 microamps. And remember that 500 microamps is a maximum, so that's across all recommended operating conditions from -40 to 85C. Now you know why you don't want to have a slow transition on the input from the perspective of power consumption. This amount of current can actually be damaging to some devices if you go too slow through this transition. There's one other reason why you don't want to transition states slowly on the input of a CMOS device, and that's because of possible oscillations. There is a not insignificant amount of inductance on the wires that connect the supply and ground internal to the device. Whenever this sudden current flows through those, it can cause a voltage to appear, and that causes your input threshold to shift. When your input threshold shifts, the output can change states, and this can happen repeatedly very quickly and produce oscillations. In more complex logic devices, you may not even see those oscillations at the output. It may only be internal to the device. That's going to draw additional power because every switching event causes more power to be drawn, and it can cause the device to operate incorrectly. Specifically in the case of clock devices like flip-flops and shift registers or counters, you can see those devices act very abnormally, like the clock was being flipped multiple times, even though you can look at your scope shot and see that you've only got one slow edge coming in. What's likely happening is that the device is oscillating internally, and you may be able to see that as some noise at the input. Now let's talk about floating inputs. I'm going to draw our inverter over here as just the normal symbol now that we've looked at how it works internally for quite a while. The datasheet is going to give a specification for input leakage current. Going back to our Nexperia datasheet, the input leakage current for this device is up to 1 microamp with a typical value of 0.1 microamp. And note that this is a plus or minus value. That plus or minus means that current could be going into or coming out of the input. It also may not be going anywhere. In fact, most of the time, the input to a CMOS device is going to be such high impedance that no current will flow at all. If this input is not connected to anything, or for example, you have a microcontroller that has an output set as an input, so this is turned off, then this line doesn't have anything actively driving it high or low. In that case, we call this a floating node. And a floating node is named that way because the voltage can float upwards or downwards, and we have no way of really knowing what that voltage is doing. If you were to connect a probe to this, then your probe is going to have some capacitance and some resistance going to ground, and that will eliminate the floating node and cause it to appear to be grounded out. It's very easy to look at a floating node and see nothing there and wonder, why is my circuit acting so strange? But as soon as you disconnect this, it goes right back to acting strange again. Essentially, this wire can be affected by parasitic capacitance. Nearby traces can cause changes in voltage. You can also receive RF signals on here, like an antenna. You can also have mutual inductance between nearby traces. Additionally, there's always going to be some level of leakage, even though it may be gigaohms, between different traces on a board. You also might have parasitics within the device or within the microcontroller. Even though this wire isn't actually connected to anything, there are a lot of possibilities that can cause that voltage to change. Now, going back to our drawing that we had earlier, recall that most devices are going to have some form of ESD protection, usually in the form of diodes. The input to a CMOS device is inherently high impedance because we're looking into the gates of two MOSFETs, and that very little current is going to be able to flow through those gates. However, most CMOS devices also have ESD structures, and these diodes typically will allow some leakage current. If there truly is nothing else connecting or affecting the voltage on the input, these diodes will quite often result in the voltage drifting to approximately VCC over 2 here, because the diodes will act a lot like resistors in parallel with capacitors. And this essentially produces a voltage divider circuit. The amount of current flowing through this is extremely small. Remember, in the datasheet we saw that the current going in and out of here is only up to 10 microamps. So as long as we can hold this at either VCC or ground and handle up to 10 microamps, then we won't have any problems. So all we really need to do is connect a resistor here. So in this case, I'm going to be tying a resistor to VCC. That's called a pull-up resistor whenever we tie it to VCC. And most commonly, this is going to be a 10 kilo ohm resistor. Now, if you want to be able to model the resistance of one of these diodes, or all of the total leakage that's going on in here, because some current will go through the gates, some current will go through these, and some current may go through other structures that could be inside the device. We look at the maximum value that the datasheet lists, which is 10 microamps, and then we can just figure out how much voltage is going to drop across our resistor. With 10 kilo ohms times 10 microamps, we're looking at approximately 0.1 volts across this resistor in the worst case. That's assuming we have all 10 microamps going through this resistor. And remember, that's the maximum in the datasheet, so we probably would never actually see that value. I would say 10 kilo ohms is a very safe value to put here. I did mention that missizing resistors is very common. So what can you do wrong with these? It's actually really common for most engineers to just select 10 kilo ohms and not worry about it. And honestly, that's not a bad way to go. However, there are circumstances where you might want to have a different size resistor. For example, if you know your driver device is going to go into a high impedance state, that's going to leave this line floating. And let's say you know the total capacitance on this line is 50 picofarads. And you want this resistor to be able to pull the line down relatively quickly. You want to keep that within the timing requirements of this next device. Then you need to calculate exactly how long it takes this to drive from a high state to a low state with 50 picofarads. There's an easy equation for this. The fall time, or transition time in general, of an RC circuit is going to be 2.2 times R times C. This is approximate, but it'll give you the 10 to 90 or 90 to 10 time for the RC charge circuit. And we can rearrange this to find what the resistor value needs to be, with R equal to TF divided by 2.2 times C. That's going to be 55 nanoseconds on the top, because that's the longest we're allowed to have for a transition time for our device, divided by 2.2 times 50 picofarads. That comes out to 500 ohms. That's probably a much lower resistance than you would have expected to be able to make this work the way you want. Now you might ask, I've done this plenty of times and I've never had a problem. And honestly, I have too. There are many devices out there running with inputs that are too slow for a CMOS device, and they don't get damaged by it. In fact, most CMOS devices are very resilient and they'll do perfectly fine. But if you're trying to design a product for mass production, these are the recommendations to try to keep things from causing problems. Now, if you don't want to be using a 500 ohm resistor because it's going to be using up too much power, and I wouldn't blame you, then what you can do is instead use a Schmitt trigger device in order to allow for slow input transitions. I'm not going to go through exactly how a Schmitt trigger input device works in this video because it's already going to be relatively long as it is, but the solution to slow inputs is Schmitt triggers. And then you can switch out this resistor to something that's more traditional, like a 10K ohm resistor, and not worry about any of this. Essentially, your Schmitt trigger device is just going to have some hysteresis added on the input, and it's going to allow for very slow transitions without ever oscillating, and the amount of power drawn will be far less because the input is designed to have those slow input transitions. I mentioned power consumption because of that pull-up or pull-down resistor, and I just wanted to show an example of that as well, because it's a question I've had asked to me. Let's say you have a 1K ohm resistor operating at 5 volts. Our input device is also operating at 5 volts. Now, how much power is this resistor going to be drawing? Well, the easy way to figure this out is going to be V squared over R, and that's just going to be 25 over 1000, or 25 milliwatts. Depending on your system, that may or may not be too much power for you. I've seen many systems where this resistor is increased very significantly to save power. So, for example, you could replace this with a 1 mega ohm resistor, and instead of having 25 divided by 1000, we're now dividing 25 by 1 million, and we're dropping down to microwatts. Significantly less power. However, there is a separate issue with doing this. Recall that there is input leakage current to the device, and there can be up to 10 microamps. If this device is operating close to that 10 microamps, then that current will most likely be drawn through this resistor, assuming the previous stage is turned off. In that event, a 1 mega ohm resistor with 10 microamps flowing through it will produce 10 volts. Now, I've been asked this numerous times, So I want to make it clear here, this device will not generate current and produce a voltage larger than the supply. What will happen is this device would drop all 5 volts, and we would only see 5 microamps actually flowing into the device, and the input would be in the low state. Although what you want is for the input to be in the high state. What you want is to set a maximum voltage drop across this resistor. I would typically choose about 0.5 volts because that will ensure that you're staying in the cutoff region of the input MOSFETs. If you choose 0.5 volts, and then we can solve for the resistor value, knowing that the voltage across it is 0.5 volts and the maximum current through it is 10 microamps. That means we can use a 50 k ohm or smaller resistor in this case. In this video, I've covered the most common issues associated with designing that come around the inputs of CMOS logic devices. In my next video, I'm going to be talking about the most common issues surrounding the outputs of these types of devices. Thanks for watching.